Once again, welcome back to Banach spaces. So in the last class, we have discussed two examples related to Banach space. One is the space, the non-linear space x is equal to r with the usual metric, usual norm. Say norm of x is equal to absolute value of x. There we have seen that this forms a this is a complete non-linear space, and so it forms a Banach space. Another examples that we have taken is say x is equal to Rn. Rn we have taken Rn. So and the norm we have taken is here norm of x is equal to summation I is equal to 1 to n xi square to power of 1 by 2. There we have seen that both are complete spaces, and so they are Banach spaces. Now let us discuss another example 3, which is of typical type. So you might have studied this example in your ring theory. There we have shown that this type of set is a maximal ideal. Say let's consider this. Consider the linear space, means vector space C of 0 1. C of 0 1. C of 0 means the set or the space of all continuous real valued functions defined on set of all continuous real valued functions defined on the interval 0 1. That is, C of 0 1 is equal to set of all f such that f is a mapping from 0 1 to r real valued, means the codomain is r and is continuous. So this is a typical example. It's C of 0 1, set of all continuous real valued functions defined on the interval closed interval 0 1. So on this set, as you have studied from metric spaces, that on any set any number of metrics can be defined. Likewise here too, on this set C of 0 1, I can define two types of metrics. One is the metric one is say norm of f, that I will call it as 1. So that is defined as supremum of absolute value of f of t, where t belongs to 0 1. This is one type of metric. See here, norm of with respect to 1 is 1. Our first norm is defined as supremum of f of t, where t belongs to 0 1, and the second norm is norm of f2. I will denote it by 2. So this is integral from 0 to 1 f of t dt. So this is called the integral metric. First one is called the maximum metric or the supremum metric. So we can clearly show that these two are norms on C01. We can easily show that these two are norms on C01. And here one important thing is, first one, this norm is, as C01 is complete with respect to norm 1 only, while C01 is not complete with respect to norm 2. We can show this easily. Okay, so first let us show that C01 is complete with respect to norm 1. Okay, so now complete means what you have to show is, say we have to take some Cauchy sequence. We have to take some Cauchy sequence, and then we have to show that Cauchy sequence converges. Say I will take the sequence, say Fn is any Cauchy sequence in C01. So then by definition of a Cauchy sequence, for a given epsilon positive, there exists a positive integer n naught such that for all integers m comma n greater than or equal to n naught, we have norm of f m minus fn, norm of fn minus fn is less than epsilon. This is with respect to norm 1. Okay, so now this implies what? So by definition of a norm, this is supremum of t belongs to 0, 1. Here you can write here itself such that fm of t, so this is fm of t minus fn of t, so is less than epsilon, Now, so using linearity property, I directly taken fm of t minus fn of t. Now this implies, since the supremum itself is less than epsilon, means each of these numbers, say fm of t minus fn of t, is less than epsilon. For this holds for every t belongs to 0, 1. Now fm of t is a real number, fn of t is also a real number, and more absolute value of fm of t minus fn of t is less than epsilon for every t belongs to 0, 1. So but this is nothing but the Cauchy's condition for uniform convergence of the sequence of bounded continuous real valued functions. So what will happen? Therefore the sequence fn must converge to a bounded function, say f on 0, 1, means fn converges to f on 0, 1. Therefore it follows that C of 0, 1 is complete under the norm 1. Now let us come to the case where we will discuss about the important cases while with respect to the norm 2, which is the integral metric, say 0 to 1 fn of t dt, norm f is equal to, this is the case. Now say this is for this I will take for n greater than or equal to 3, say I will consider the sequence of functions, say fn of t is equal to, is very important, fn of t is equal to, this is 1, fn of t is equal to 1 between 0 less than or equal to t less than or equal to 1 over 2, and I will define fn of t is equal as minus nt plus n by 2 plus 1 in the interval 1 by 2 less than or equal to t less than or equal to 1 by 2 plus 1 by n, 1 by 2 plus 1 by n. So in the interval say minus n 1 by 2 to 1 by 2 plus 1 by n, fn of t takes the value minus nt plus n by 2 plus 1 and 0. So in the interval 1 by 2 plus 1 by n less than or equal to t less than or equal to 1. So this is the fn of t we defined. Say now, so if you want to write a diagram for this, say you take x-axis as t and the y-axis as say fn of t. So when, see here, when t is 0, when t is 0, fn of t is 1, say this is the value 1, so it is the value 1. So I will split this as of 1, here of 1, okay. So now it takes the value takes the value from 0 to 1 by 2. So t takes the value from 0 to 1 by 2 means here up to, here its the value is 1. Thereafter it is decreasing between the value 1 by 2 to 1 by 2 plus 1 by n. So it takes the value say like this, the graph will come like this. So in the interval 1 by 2 plus 1 by n to 1, the value of f of fn of t is 0. This is 0, okay. This is the 1 by 2 1, this is off, this is 1. Okay, this is the graph. From the graph itself we can see that the function, the function we have constructed is definitely a continuous function. So it is a continuous function, in particular on the interval we have taken is 0, 1. Now this fn itself is, we can see that this fn itself is a Cauchy sequence. Fn is a Cauchy sequence, because whichever the sequence we consider, so our aim is to show that C of 0, 1 is not complete with respect to integral metric, means the Cauchy sequence must not converge. This Cauchy sequence must not converge, or completeness means every Cauchy sequence converges. In particular, this is the Fn is the sequence we have constructed. So we show that it must be Cauchy sequence. There we will show that it is not complete. So showing that this is a Cauchy sequence follows like this. See here. Say if I take m comma n greater than m is greater than n, greater than or equal to 3, then what will happen? Norm of fm minus fn, that is equal to integral 0 to 1. The definition is fm minus fn of t dt. So this is equal to, by using a property, linear property, because these are all linear functions. So 0 to 1 absolute value of fm of t minus fn of t dt. So I will split the interval 0 1 to as 0 to 1 by 2 plus 1 by 2 to 1. So fm of t minus fn of t as it is. Now, so 0 to 1 by 2, fm of t takes the value as, so the fm of t is 0 to 1 by 2, 0 to 1 by 2, the fm of t or fn of t is, the value is 1. So what will happen? Fm of t takes the value 1 and fm of t takes the value of 1 into dt. So the left is I written as it is, 1 by 2 to 1 fm of t minus fn of t dt. So the first becomes, this one first integral becomes 0, 0 plus. Now 1 by 2 to 1, so this is less than or equal to, because I taken mod absolute value of fm of t minus fn of t. You know that it is mod of x minus y is less than or equal to mod x plus mod y. So I use the property. So I split this as off to 1 integral over off to 1 fm of t plus off to 1 fn of t dt. You call this as number 1. So now what will happen? Now I will take the particular value 1 by 2 to off to 1 fm of t. Off to 1 fm of t, I split this as off to 1 by 2 plus 1 by m fm of t dt plus 1 by 2 plus 1 by m to 1 fm of t dt. So this is equal to off to 1 by 2 plus 1 by m. The value of fm of t is minus mt plus m by 2 plus 1 into dt. The other is fm of t becomes 0 in this interval, 1 by 2 plus 1 by m to 1, it becomes 0. So this is off to 1 by 2 plus 1 by m. So this becomes minus mt plus m by 2 plus 1 into dt plus this is 0. Okay. So I remove the absolute symbol or modulus symbol, because so in the interval 1 by 2 to 1 by 2 plus 1 m, so this value is either 0 or positive, 0 or non-negative, 0 or non-negative. So the absolute value becomes like this only. Okay. So I remove the absolute value symbol. So now just I apply. So now what we done is here. So just integrate this. Integrate this is minus m I taken outside, and we have done the integration and applied the upper and lower limits. So we can see that by a simple calculation, we can see that the value will be 1 by 2m. So 1 by 2 to 1, 1 by 2 to 1, fm of t is 1 by 2m. Similarly, we can show that 1 by 2 to 1 absolute value of fn of t is also 1 by 2m. Therefore, if we substitute these values in 1, we can see that norm of fm minus norm of fm minus fn is less than or equal to 1 by 2m plus 1 by 2n. So the both tends to the sum tends to 0 as m and n tending to infinity. Therefore, fn is a Cauchy sequence. Now we have constructed the Cauchy sequence in C of 0, 1 with respect to norm 2. Now we'll check whether the constructed Cauchy sequence is convergent or not. Suppose it is convergent. Let's assume that it is convergent and converges to some function, say g, in 0, 1, in C of 0, 1. Then what will happen? Then if fn converges to g of t, then g of t takes the value 1 when in the interval 0 to 1 by 2, and it becomes 0 when in the interval 1 by 2 to 1. It means that takes two different values. G is taking two different values now in this. Therefore, what you can say, G is not continuous at G is not continuous at the point of, because at the point of it takes the values 1 once, and at the same at the off it takes the value 0. So G taking two values at the value t is equal to half. So G is not, therefore G is not continuous function. G is not continuous function means G cannot lies in C of 0, 1, because C of 0, 1 contains set of all continuous real valued functions. So the sequence fn which is convergent to G, if you assume that, then that G doesn't belongs to C of 0, 1. Therefore fn is not convergent. Since fn is arbitrary, under particular function which is not convergent, therefore we can declare that C01 is not a Banach space. C01 is not a Banach space. This is a very good example where we can show that although it is a non-linear space, but it failed to become a Banach space. Okay, let us discuss another example. Say example 4. Example 4. Say here too, I'll consider one important and interesting example here. So you all know that what's meant by a LP space. LP, say 1 less than or equal to p less than infinity. 1 less than or equal to p less than infinity. So what is this LP? LP, you know that it is the space of all sequences. The elements are here all sequences, x1, x2, etc., xn, infinite sequences. Okay, they are all infinite sequences of scalars which may be real or complex, such that what is the condition? So summation n is equal to 1 to infinity, xn power of p is finite, and the norm is used here is norm of xp is summation I is equal to 1 to infinity xip power of 1 by p. This is the norm you have considered. Okay, so in metric spaces you know what is meant by an LP. So here, there too we have taken the same definition. Instead of a norm here, there we have taken the distance function d. Okay, so now clearly we can see that LP is a linear space. LP becomes a linear space with respect to two linear space conditions. One is vector addition and scalar multiplication. Say that is x plus y is equal to say x1 plus y1, x2 plus y2, and so on, xn plus yn, and so on. One is vector addition. The other is the scalar multiplication is alpha into x. Say alpha into x is alpha into x1, alpha into x2, etc., alpha into xn, and so on, where alpha is a scalar. Here x and y are the elements of LP, which are the infinite sequences, so xn and so on, and y is y1, y2, and so on, yn. Okay, so these are the elements. Now, so we can clearly see that LP itself is a non-linear space. Because see here, I'm directly taking the written document to avoid the time. So now LP is a non-linear space because now you can see that each xi is non-negative. Absolute value of each xi is, you can see that it is non-negative means, so we have norm of xp is definitely non-negative because norm of xp is the summation of these non-negative scalars. So this becomes, since each xi is non-negative, so norm of xp is also non-negative. Suppose the second condition, let's come to the second condition. Now norm of xp is 0. Now norm of xp is 0 means, so summation I is equal to 1 to infinity xi power of p whole power of 1 by p is 0. Now the sum itself is 0 means whole power of 1 by p is 0 means this itself is 0. So the sum itself is 0 means absolute value of xi power of p is 0 means absolute value of xi itself is 0. This means each xi is 0. Each xi is 0 means x having these as the coordinates itself is 0 means norm of xp is 0 implies x itself is 0. So this is the second condition of the norm. And if it come to the third condition, what is that condition? Norm of x plus y of p is summation I is equal to 1 to infinity xi plus yi power of p whole power of 1 by p. So using Minkowski's inequality, we can show that this is less than or equal to summation I is equal to 1 to infinity xi power of p whole power of 1 by p plus summation I is equal to 1 to infinity yi power of p whole power of 1 by p. Now this is nothing but norm of xp plus norm of yp. Therefore norm of x plus norm of y of p is less than or equal to norm of x of p plus norm of y of p. So similarly norm of alpha into x of p, that we can prove it to be mod of alpha into or absolute value of alpha into norm of xp. Therefore LP 1 less than or equal to p less than infinity is a non-linear space. Now it's a non-linear space. Now the important thing is, here our aim is to show that it is a complete non-linear space, or in other words it's a Banach space. Suppose now we consider xn to be any Cauchy sequence in LP. I'll take xn is a Cauchy sequence in LP. Now xn is a Cauchy sequence in LP means what? Here each xn is a sequence of scalars, right? x1 here xn is a, this one it like fn. Fn means f1 is also a n tuple of scalars. Here each xn is a n tuple of scalars, though we can write the typical element say xm by, what will happen, itself is a n tuple of scalars means x1m, x2m, etc., xnm and so on. So there it satisfies the condition like summation n is equal to 1 to infinity xn m power of p is less than infinity. This is the condition for an element to be in LP. Now, so this is now xn is a now we have taken xn to be a Cauchy sequence in LP. So by definition of a Cauchy sequence, what will happen? As you know, there exists a positive integer m naught. There exists a positive integer m naught such that m comma n greater than or equal to n naught implies a norm of xm minus xm is less than epsilon. So you call this as number 1. So in particular, if you take for n greater than or equal to n naught, norm of xn minus norm of xn naught, you can take any of the numbers. So norm of xn minus instead of m we have taken the particular n naught, so minus xn naught is less than epsilon. You call this as number 2. Thus what will happen if n is greater than or equal to n naught, norm of xn of p is xn minus xn naught plus xn naught. So I just add and subtract xn naught. So use the triangle inequality. So we can see that from 1 we can see that it is the value is less than epsilon. First term is less than epsilon plus norm of xn naught of p. So this is equal to, I put a as the number epsilon plus norm of xn naught of p. So then what will happen? A is positive. A is positive because epsilon is positive and this number is always definitely non-negative. So positive plus a non-negative means it's definitely a positive number, and norm of x and p is less than A. For n we have taken to be n greater than or equal to n naught. You call this as number 3. Now from 1 what will happen? So n comma m greater than or equal to n naught implies norm of xm minus xnp is less than epsilon. This implies xm minus xn I raise to the power p, so it becomes epsilon raised to p. So if we raise to the power of p, that 1 by p fraction get cancelled, so you will have summation I is equal to 1 to infinity. So this is xim corresponding to the element xm, and corresponding to the element xn, xin power of p is less than epsilon power of p. So now this implies, so summation itself is less than epsilon p means this terms, each of the terms must be less than epsilon power of p. So I takes the value 1, 2 and so on. So this implies each of these numbers xim minus xin less than epsilon, because p I can remove the power p or rising to the power 1 by p. Okay. So now xim minus xin less than epsilon means this shows that for a fixed I, this is a fixed I. So the sequence xin is a Cauchy sequence in C or R. But both R and C are complete. Therefore, each of these sequences converge to a point, say Zi in C or R. Zi may be C or R. Next is, so let Z be the sequence which is having the coordinates which are the converging points. So Z is equal to Z1, Z2, etc. Zn, where the type of things we have discussed in while proving Rn is a Banach space. Now, so we consider this is a n tuple of scalars. This is a sequence of n tuple of scalars, but we don't know whether this element is in LP or not. That's the main thing. So if you assume that this is in LP, then our aim is to only show that xn converges to Z, but we don't know whether this element x, Z lies in LP or not. So for that we need to verify whether Z is in LP. Z is in LP means whether the condition of a element to be in LP will satisfied by Z or not. So I'll prove this also. So we show that Z belongs to LP. So now from 3 what will happen? We have n greater than or equal to n naught implies norm of xn p is less than a power of p. So xn means summation I is equal to 1 to infinity xin power of p is less than a power of p. Thus, hence for a fixed positive integer L, if you take fixed positive integer L, we have definitely, so summation I is equal to 1 to L xin power of p is less than a power of p, because it's for the infinite sum means there is some number which is maybe very big that may be chosen L. After certain stages definitely this is less than a power of p. Now, but for a fixed, but for I is equal to 1 to L, we have xin converges to where? We have xin converges to Zi as n tends into infinity. Hence, letting n tending to infinity and noting that this is limit is a this theorem you have taken up. Limit n tends to xn plus yn is x naught plus y naught, and xn is less than or equal to yn implies x naught is less than or equal to y naught, where these are the sequences where x is equal to xn and y is equal to yn are the sequence of scalars such that limit n tends to infinity xn is equal to x naught and limit n tends to infinity yn is equal to y naught. Now we have summation I is equal to 1 to L. What will happen? Zi power of p is less than a power of p. L takes the value 1 to n. So it follows that if this condition holds true for any L means, so it takes for the infinite sum also. Summation I is equal to 1 to infinity absolute value of Zi power of p is less than a power of p. A power of p means it is a scalar, so which is a finite quantity definitely. If it is a finite quantity means summation I is equal to 1 to infinity mod Zi power of p is less than infinity means the Z belongs to LP. We have shown that the element Z which is the which has the coordinates which are the converging points of the sequences is an element of LP. Now the final step is to show just that the sequence, original sequence what we are consider. So this is the original sequence that we have considered converges to Z. So again we'll consider from 1 for n comma m greater or equal to n naught, we have, this is the condition we have taken in 1, norm of xm minus norm of xm minus xn power of p is less than epsilon raised to p. This implies by definition of a norm in LP, summation I is equal to 1 to infinity, xim minus xin power of p is less than epsilon raised to p. Hence, for a very positive integer L, we have this condition. Summation I is equal to xim minus xin power of p is less than epsilon power of p, because it is holds good for the infinite sum itself. Now, letting m tending to infinity, and using the fact that limit m tends to infinity xi power of m is nothing but zi. So, we obtain summation I is equal to 1 to L zi minus xin power of p is less than epsilon power of p for n greater than or equal to n naught and for all positive integers L. And so what will happen? Summation I is equal to 1 to infinity xin. So I taken because mod of x minus y is same as mod of y minus x. So absolute value of xin minus zi power of p is less than epsilon p. This is nothing but what? Norm of xn minus z raised norm of xn minus z power of p is less than epsilon power of p. This implies norm of xn minus z p is less than epsilon. Means what? Xn converges to Z. So the original sequence Xn which considered in LP converges to point Z which is in LP itself. Therefore LP is complete. And you know that a complete space is a Banach space, and so LP is a Banach space. Similarly, L infinity is also a Banach space. These are the few examples that we have discussed. So, and in the next class we will discuss the other topics like subspace of nonlinear space and theorems thereon. Okay, thank you.